Hi, this is Simon Apers. I'll be talking about a joint paper with Ronald titled Quantum Speedup for Graph Sparsification, Cut Approximation, and Laplacian Solving. I'll start off by talking a little bit about graphs, and I'll make the following bold claim, which is that graphs are nice. Graphs show up all over computer science, discrete math, biology, and so on. And they are very nice mathematical objects to describe relations, networks, groups, etc. Now, an even bolder claim is that sparse graphs are nicer. Right? They take less space to store and less time to process, in the sense that if you want to solve a problem on a graph or estimate a certain quantity of a graph, then typically this will be easier for sparser graphs, where a graph is sparser if it has less edges. So an example of this phenomenon is that expanders, which are kind of sparse approximations of the complete graph, are much more interesting both mathematically and in applications than complete graphs. Right, so this raises the general question whether we can compress general graphs to sparse graphs. This is basically the domain of graph sparsification. So in graph sparsification, we'll be considering graphs, and so for the purpose of this talk we'll be talking about undirected weighted graphs G with node set V, edge set E, and non-negative weights W, and the graph has n nodes and m edges. Okay, so these are kind of important quantities here. Now by graph sparsification, what do we mean by this? We start from some given graph G, which can have a lot of edges, and the goal is to output a sparser graph H, which will typically be a subgraph of G, potentially with reweighted edges, such that, okay, H has significantly less edges, so it's a sparse graph, but it preserves certain interesting quantities of G. So what are interesting quantities? They were thinking about things such as extremal cuts, eigenvalues, properties of a random walk on the graph, etc. And as it turns out, many of these properties are captured by what we call quadratic forms in the graph Laplacian, right? So if LG denotes the graph Laplacian, then quadratic forms of the form x transpose LGx and x transpose LG plus x, where LG plus is the pseudo-inverse of the Laplacian. These are what we call the quadratic forms in the Laplacian, and it turns out that a lot of these properties can be expressed as quadratic forms in the Laplacian. Now maybe just to clarify, when we say graph Laplacian, we mean the following matrix LG, which equals D minus A, where capital D is the diagonal matrix containing the weighted degree of a node, if you want, basically the sum of all the outgoing weights. And A is the adjacency matrix, where entry ij equals to the weight between edge I and j, and we'll set wij equal to 0 if there's no such edge. Alright. So given that a lot of these interesting quantities are captured by these quadratic forms, the notion of spectral sparsification kind of makes sense, because it basically asks that we sparsify a graph while approximately preserving all quadratic forms. Right? So given a graph G, we want to return a sparser graph H, such that the quadratic forms of H for every x are epsilon approximations of the quadratic form of G. And this basically implies that properties such as the min cut and so on of H will be epsilon approximations of these properties in G. Now equivalently, we could ask that the quadratic forms in the pseudo-inverse of the Laplacian is epsilon approximated. So these are two equivalent definitions of what we call epsilon spectral sparsifiers. Now, of course, this notion also seems very nice, right? Because we really preserve a lot of properties, but does it make sense, right? Can we actually find a sparser graph H that approximately preserves all these quadratic forms? And it turns out that we can, and we can actually go pretty sparse. So in a long line of work starting by Karger, then there was Benzer-Karger, Spielman-Teng, and then Batson-Spielman-Srivastava, and there's actually many more works on this subject. The following was established. First, every graph has an epsilon spectral sparsifier h with the number of edges O tilde n over epsilon squared, where the tilde is hiding polylog vectors. Right, so this is nearly linear in the number of nodes. And in fact, this last paper, this Batson-Spielmann-Srivastava paper, showed that this tilde is not even necessary. You can actually get a sparsifier with n over epsilon squared edges up to constants. But I'm putting the tilde here because the second point is kind of interesting for this talk, which says that if we don't care about log factors, then we can find this epsilon spectral sparsifier h in time O tilde m, which is what we call near linear in the size of the graph, right? We call it m is the number of edges, so in some sense it's the description size of the graph. And so near linear in the description size, we can find this epsilon spectral sparsifier with only approximately n over epsilon squared edges. Now this theorem and the many forms that it takes is a fundamental building block of many near linear time cut approximation algorithms, and it's a crucial component of the breakthrough Laplacian solver by Spielmann and Teng, which basically solves Laplacian systems in near linear time. And in fact, the specific notion of spectral sparsification was proposed by Spielmann and Teng in their 04 paper, where basically the goal was to construct a near linear time Laplacian solver. Now what's our contribution here? So what do we have to say here? So me and Ronald, we're actually doing work on quantum algorithms, so it made sense to look at sort of quantum algorithms for sparsification. And what we found is the following. We found a quantum algorithm that constructs an epsilon spectral sparsifier h in time O tilde square root mn over epsilon. Right? So given query access to the graph, right? So for a given node, we can ask what is your first neighbor, what is your second neighbor, and so on. Given such access, we can construct the epsilon spectral sparsifier in sublinear time, right? Because for dense graphs, classically we would need time scaling as n squared, whereas this would scale as n to the 3/2. Then we show that actually we can do much better, right? We show a matching lower bound, which is matching up to polylog factors, and finally we discuss a slew of applications, and then we find quantum speedups for cut approximation, Laplacian solving, and many more problems. So I'll start off by discussing our quantum algorithm, but to do so I have to kind of sketch what's known and how people sparsify classically. So sort of blueprint of what we call sparsification by edge sampling, which is a blueprint of many sparsification schemes, is the following. We start by associating a probability PE to every edge E, so this is a probability between 0 and 1, and we keep every individual edge E with corresponding probability PE, and we rescale its weight by 1 over PE. This ensures that the expected value of an edge weight is equal to its original edge weight, and as a consequence, by linearity, we get that the Laplacian LH, its expectation, since LH is just a linear combination of what we call edge Laplacians, weight with WE, it implies that the expectation of the Laplacian of H is actually equal to the Laplacian of G. So what remains to be done is to ensure concentration, right? Because we don't just want that the expectation is equal, we want that effectively these values are close. And here we can use a theorem by Spielmann and Srivastava, which is kind of cool. They showed that, okay, so let me clarify clearly. What we can do is we can put PE equal to 1 for every edge. Then we just keep all edges, and clearly LH will be equal to LG, and so we have concentration. But of course we want a sparser graph, so we want to make all the PEs as small as possible. Now what Spielmann and Srivastava showed is that it suffices that we give a high PE to the edges with a high effective resistance. And vice versa, if an edge has a low effective resistance, then we can give it a small PE. So we don't have to keep it with large probability. Now maybe to clarify, by effective resistance, I mean, so given a pair ij, we first replace all the edges by resistors, and then we measure the resistance between nodes I and j. So in this case here, the resistance would be 1, but between these two nodes, the resistance would be smaller than 1, right? Because the effective resistance between two nodes will effectively be small if there exist many short and parallel paths from I to j, right? So if you take, for instance, this edge, then there's actually a lot of replacing paths, basically n, which have length 2. And this will imply that this edge has small effective resistance. And this is basically what we expect, right? This edge is very important, and it should get a large sampling probability, which is reflected by it having a large effective resistance, whereas these edges have small effective resistance, and indeed they are kind of redundant. But of course, how do we identify these high resistance edges? And here we use a result by Kutis and Zhu from 2014, who showed that a certain object called a graph spanner must contain all the high resistance edges. Right? So Spielmann and Srivastava showed that the important or critical edges are the high resistance edges, and Kutis and Zhu, they then showed that a graph spanner must contain all high resistance edges and hence all the important edges for sparsification. But what is a graph spanner? So a graph spanner is again a subgraph with little edges, basically O tilde n edges, such that all the distances, where we use the shortest path metric, are stretched by a factor at most order log n. So basically, if we take a subgraph, then the distance will only increase, and we want that the distances do not increase too much, right? So let's say that we take this edge, which has distance 1 in G. It's dropped in F, but we need a sort of replacing path, and here we have a path of length 4, so we see that the stretch on edge E is 4. And so a spanner basically requires that all distances are stretched by a factor at most log n. So maybe for completeness, I'll add that in principle this is a arbitrary factor, so we talk about k spanners where the stretch is at most k, but we'll only care about k equal to order log n. So this gives us the following iterative sparsification algorithm. We start by constructing a bunch of spanners. So basically we construct O tilde 1 over epsilon squared spanners, where we start by constructing a spanner, then we remove it from the graph, and then we construct a spanner in the remaining graph, and we kind of reiterate this, O tilde 1 over epsilon squared times, and we keep all these edges, right? Because recall that these spanners identify the important edges. And then the next step, we basically throw away any of the remaining edges with probability 1/2, right? Because we know that these edges are kind of less important because they don't show up in the spanners, and so we can downsample them with probability 1/2, and then we double their weight basically to keep their expected value equal to their weight in the original graph. And this leads to the following theorem, combining results by Spielmann, Srivastava, and Kutis and Zhu. With high probability, the output of this algorithm is an epsilon spectral sparsifier with, in expectation, m over 2 plus a little bit edges. Right, so we're basically halving the number of edges. And if we repeat this order log n times, right, so we start with a graph with m edges, and we have m over 2 edges, and so on. And by transitivity of the notion of spectral sparsification, we just have to choose the epsilon here slightly smaller, and then we'll see that the final graph is an epsilon spectral sparsifier of the original graph with only O tilde n over epsilon squared edges. Now our quantum sparsification algorithm builds on this scheme, and we kind of have 3 sort of steps that we need. Right? So we start by constructing a quantum algorithm to build spanners. Then we have to use something called a k-independent oracle, and finally we use a bootstrap trick to kind of put the dots on the I. So a quantum spanner algorithm. An easy theorem, relatively easy theorem, is the following. There exists a quantum spanner algorithm, which is basically a quantum algorithm for constructing a spanner, which has query complexity O tilde square root mn. Right, so the query complexity basically measures the number of queries that we have to do to the graph. So recall that a single query is asking, given node I, what is its kth neighbor, something like that. So classically, it's not hard to show that you need you approximately need m queries. Now quantumly, we can go sublinear, and we can get something like O tilde square root mn. This is not too hard to show. So if we start from the greedy classical spanner algorithm, which basically does this, it starts from Yeah, so you have query access to a full graph, and then you have some spanner which you're going to build up. So you start you start with an empty spanner f, and you iterate over every edge of the original graph. And so for every edge, a necessary condition is that in the spanner there is a replacing path of length at most log n, something like that. And so what we do is we iterate over all the edge of the original graph, and whenever we see that there is no replacing path of length at most log n, so basically if the shortest path between I and j and f is larger than log n, then this condition is violated, and we add the original edge to f. So we add an edge to f, which then ensures that the distance is okay. And we keep on reiterating over all the edges of the original graph, and finally we can show that the resulting graph is a spanner, and actually can also show that we didn't add too many edges. Now, a corresponding quantum greedy spanner algorithm is the following. Again, we start from an empty spanner algorithm, and we basically do the following. We use Grover search to search over the large graph and the set of edges of the large graph, and we search for an edge that violates this condition, right? And if we find such an edge, then we add it to f, and we keep on reiterating this until no more edges are found. And it's not too hard to show that this gives us the O tilde n edges of the spanner using O tilde square root mn queries. So this provides a nice quantum algorithm which has sublinear query complexity, but we kind of want a bit more in this paper. We want to also prove results on the time complexity, and so we take a bit of a less easy route. What we do is we very roughly combine a spanner algorithm by Thorup and Zwick, which builds on shortest path trees, and we combine that with a quantum algorithm for constructing shortest path trees by Duhr, Heiligmann, Heuer, and Malla. And that's how we get a quantum spanner algorithm, which is actually time complexity O tilde square root mn. So now we can just combine this with the classical algorithm, see what it gives. So in the first step we use a quantum algorithm to construct O tilde 1 over epsilon squared spanners, and now we kind of drop half of the remaining edges, something like that. Now the problem is that if we do that, so recall that the initial graph, we have access to the initial graph through its adjacency list, right? So we're assuming that we have some sort of query access to that adjacency list, but we can't fully store it because we want a sublinear algorithm. So that's okay, but after a single step we want to throw out half of the edges, but that means that the remaining graph after one iteration still has approximately m over 2 edges, and so we can't explicitly store it or explicitly describe it, so we have to kind of be a bit smarter. But the problem is we don't have time to store random strings of that size, or let alone the intermediate graphs, and so we have to be a bit smarter. And so what we show is that it suffices to use a very nice construction by Christiani, Pag, and Thorup on efficient k-independent hash functions, and this kind of seems to solve the problem nicely. Right, so if you combine these two ingredients, then we get our quantum iterative sparsification algorithm, which uses the quantum algorithm to construct these spanners, and then it constructs this k-independent oracle in the second step. It's kind of a data structure, so we have to construct it. And we can use that to implicitly mark which edges are still present in the graph and which are not. The complexity here is O tilde square root mn over epsilon squared per iteration. This is dominated by this first step. Constructing a single spanner takes times square root mn, and we have to construct 1 over epsilon squared of these. And we need O log n iterations, so this gives us the following theorem. There exists a quantum algorithm that constructs an epsilon spectral sparsifier with O tilde n over epsilon squared edges in time O tilde square root mn divided by epsilon squared. So this is good, but it's not quite what we promised. We promised that we would get something like square root mn divided by epsilon. And to get there we need another trick. It's kind of a nice bootstrapping trick to improve this epsilon dependency. So what we do is we start by creating a rough spectral sparsifier for epsilon constant, something like say 1 over 100, and then we use the effective resistances of H, which are constant factor approximations of the effective resistances of G, because it's a spectral sparsifier, and we use these constant factor approximations basically to sample edges from the original graph. So we use a sort of rough estimate to give us rough sampling probabilities, but it turns out that this is sufficient. And basically, if we then combine this with something like Grover search, then we actually can find among these m edges of the original graph these n over epsilon squared edges in times square root mn divided by epsilon, which is what we promised. Alright, we also prove a matching lower bound, which is matching up to polylog factors. So the intuition of the lower bound is the following. If in an abstract setting we want to find k-marked elements among capital M elements, this takes omega square root mk quantum queries, and this is tied to using Grover search. Hence, and I'm putting this between quotes, if you want to find these n over epsilon squared edges of the sparsifier among m edges of the original graph, then this should take square root mn divided by epsilon quantum queries. But of course, this hence is kind of hiding a lot of stuff. For instance, it involves hiding an unsparsifiable graph. This is kind of a graph that has n over epsilon squared edges and cannot be further sparsified. It's a construction by Andoni, Chen, Krautgamer, Kin, Woodruff, and Zhang from 16. And we hide this unsparsifiable graph in a larger graph, and then we prove a quantum lower bound on the outputting of a constant fraction of the sparsifier. And here we use a quantum lower bound on a relational problem. We didn't know that this existed, so we asked Belov and Lee, so this is Alexander Belov and Troy Lee, whether this existed, and they said, like, we don't think this exists, but they were so kind to prove it for us, and so this is a very recent paper by them. And so finally, I'll just briefly mention some of the applications. So in cut approximation, we know that there are classical near linear time algorithms for things such as min-cut, min-st-cut, sparse cut, and so on. So we can find a quantum speedup in the following way. First, we use a quantum algorithm which has complexity square root mn over epsilon to create an epsilon spectral sparsifier H with only n over epsilon squared edges. And this epsilon spectral sparsifier, epsilon, like the min-cut, min-st-cut, and so on of this H, is an epsilon approximation of the min-cut and so on of the original graph. So now it suffices to use a classical near linear algorithm to approximate these cuts in the sparsifier H. But since this algorithm is near linear, this takes time only O tilde n over epsilon squared. So this gives us a quantum square root mn over epsilon time approximation algorithm for epsilon approximating things such as the min-cut, min-st-cut, sparse cut, and so on. For Laplacian solving, we get a sort of similar story. So we start from some Laplacian system Lx equals b, and by Spielmann and Teng we know that we can approximate x in time O tilde m, where m is the number of non-zero entries of L. So if we combine this with a sparsifier algorithm, then we get a quantum algorithm to sparsify G to H first, and then we basically solve the Laplacian system in H, and by its definition of a spectral sparsifier, we know that the solution of this system will approximate the solution of the original system. So this gives us a quantum algorithm for Laplacian solving, which has complexity square root mn over epsilon. And of course, this gives a slew of other applications, such as approximating effective resistances, cover times, eigenvalues, and so on. I'll just end up by summarizing a little bit. So we constructed a quantum algorithm for spectral sparsification in time O tilde square root mn over epsilon. We prove a matching lower bound up to polylog factors, and we show a number of quantum speedups for related applications. We have a couple of nice open questions. One is we prove the lower bound for sparsification, but ultimately we would like a lower bound for the applications. Like, can we prove a lower bound of square root mn over epsilon for approximate min-cut or Laplacian solving? This is an open question that we haven't been able to resolve yet. And second, our lower bound proves that our sparsification algorithm is tight, but this is only for weighted graphs, because our lower bound makes explicit use of the fact that we have weights in the graph. And so we have a strong suspicion that we can actually do better for unweighted graphs. So with that, I'll end, and I'll thank you for looking at this talk, for your attention, and I hope that everybody can stay safe. Take care.